All right, so let's begin. Where I work is I work at a prototype company, which is called Rapid Sheet Metal. And what I'm going to go over is some of the things of the common things that we see, and as a manufacturer, we always have to, tidy up and fix to prepare a proper DXF flat for the laser, which then can be formed, which then can be welded in a very high tolerance manner. We dedicate and prototype, so that just means all we mostly focus on is first runs. First runs in the sheet metal industry is very difficult. It's probably the hardest part. Production houses like the repeat parts because it's more of a, that's why you run a lot of 5,001 part or 1,001 part, because you don't have to do the setup and the engineering and all the things that we do on a daily practice.
Excuse me.
What?
You're going to do some pertinent?
We do at the end the pertinent stuff, but we're also I'm gonna go through this pretty quick. We're gonna make this available online because there's a lot of step-through procedures, but I always like to kind of cut through the end and show you what it does, and then maybe go back into detail if you guys want more detail on it. But basically, I'm going to show you a lot of different things that I really find interesting, and hopefully, at least my goal is to you guys all walk away using one of these new techniques. If I do that, I'll be successful. Last month, we quoted 25 unique SolidWorks part files. So when I say a lot of part files, I mean that's 100 a day. Well, I'll punch in, Monday, and when I punch out, 100 unique part files went out as quotes to different customers all over the country. So we definitely see a wide variety of designers and how sheet metal is designed today. This is a map. Probably not supposed to show you all of this, but year to date we've done 16,000 different orders. So when I talk about customers, I just want to give you the background. It's not really just people in New England or people in Nashua. This really is more of a feel of what we see throughout the whole U.S. and about some of the common practices, I think could be done a little in better detail. This is the review what we're going to go over. We're going to go over countersinks, which is pretty basic, but there's some tricks that I think I can show you to help prepare the through hole on a countersink. Hardware, sheet metal hardware. Who in the room has actually used hardware, has a hardware library? And do you guys, one very important question is how many FeatureWorks are out there versus regular standard SolidWorks seats? FeatureWorks is a higher level of SolidWorks. So FeatureWorks has a thing called the toolbox. And the toolbox, everyone's used the toolbox. It kind of helps out in some ways, but again, we find that most people have the standard seat of SolidWorks where you are downloading parts from PEM or from McMaster and having to put your own mates on them. And I think that's probably the majority of you guys, I hope. So we'll go over mates and things like that. We'll go over some of the SolidWorks defaults that we can change to help improve the sheet metal. Custom properties, a very quick way to add finish notes and other details to your prints in a very organized way. The welded box and cover with equations, which is you can design a box and a cover one time and be able to reuse it multiple times through equations. Advanced bend reliefs and examples. And then we'll also show you videos of sheet metal actually being formed with offsets and bump forming. We'll give you some review on how to design faster, and then pictures of before and after, the design versus after, what we do on the manufacturing side. You start right off with countersinks. As you can see, this is a countersink in a very thick plate, which usually causes no issues on the top of the screen. When you get to sheet metal sizes, a common sheet metal size is 18 gauge, which is 0.47 thick. As we can see, as the larger countersink goes, that through hole is then cut off. We see a lot of designs start and stop, and a lot of the times the through hole in the adjusting part is too small, and then you have to have a post machine or your local shop open that up. And especially with these undercut screws, then you're trying to find a very special undercut screw to get your design to work or your countersink to sit flush. And hopefully this will bring more light to that. This is a section cut. So you can really see how that screw extends down. Right here is where the conflict of your mating part usually happens, and if we can get you a proper through-hole size on your parts up here, then we can get you a proper through-hole size for your adjusting part or your machine parts, then you won't have to run into this issue. This area right here in sheet metal should be about 20% of the material thickness. And to really get a nice straight countersink without this coming into a theoretical point and having that burr on the end, you have to make that through hole larger sometimes if the material is thin. This is another example of what we commonly see is we see countersinks like this just because that's what SolidWorks Hold Wizard gives us. And, again, because it's sheet metal and SolidWorks is thinking more of, that you should have a thicker plate to begin with, this is turned into a common issue. A lot of times print will dimension a through hole on a countersink, where the through hole is not really the part that locates it, it's really the major diameter. As that screw gets tightened down, the major diameter itself locates it. And as you can see, a through hole dimension can be off by a substantial amount. Down here you see the through hole of how it was done by SolidWorks is 143, but the true through hole should really be 160. So it's about 20 thousandths off, and that's pretty big tolerance. But again, it's all about the functionality of the screw as it goes into the part. So there's a very advanced calculation for this, and we used to trig this out, but to find this answer very fast is what I'm going to show you now. So here we can see that instance of that going down to a theoretical point, which really isn't common practice. If we wanted to trig this out, we could, but a very basic, simple thing is to go ahead and just make a sketch in the back. Just covering all the countersinks, and then we need to do that 20% of material left over, so we take the material thickness and we multiply it by 0.2. Here we go, 0.047 times 0.2. And it gives us our 20% of material. And then we can come onto this face and take our dimensions. We'll see that the proper through-hole size should be 214. We can now go back to our hole wizard and cut that out at 214 and adjust it, which probably should be the proper way. Or we can simply just convert these faces real quick as sketches and do a cut through all. I'm just using the convert feature. I have a lot of keyboard shortcuts. And now we have a proper countersink. So as far as back to a manufacturer, this is what we have to do. I have 11 engineers that work under me, and this is what we scan for as these models come in. Does the countersink have the proper through-hole size? If not, we go and do a post-cleanup. As a designer, you should be aware of these things, but truly your manufacturer will take care of these things for you. But they are out there, and this is part of what we as manufacturers do to clean these things up. This is an example. This happens a lot more than you would think. Whereas what did they tolerance? +5, -1. They actually dimensioned out the through hole. That does not drive the location of the screw. And as you can see before, this through hole is actually not achievable. It should be about 20 thousandths larger. So as common feedback to our designers at Rapid Sheet Metal, we actually work really close and try and educate our customers as much as possible. And we see that feedback loop just get stronger and stronger, and we try and help you guys create better products. Just taking pictures. Our website is actually really helpful. we're trying to put as much as we can on it. Now that we have Wi-Fi, this is our website. There is just a ton of information on here. If you go to resource links, you'll see that we have a bunch of tech tips and plating specs and hardware and some videos that really help out. The next topic that we're going to jump into is hardware. Again, it sounds like some of you have been using the hardware. The hardest thing really is to find out what material thickness that dash number is for that S440, and we make that very fast. These are the thread types, these are the material thickness, and this is the shank code, or that last dash number that should be used. Aluminum. We should always try and use stainless steel hardware in aluminum parts. That is for the plating process to be done. When we chromate something, you can actually put the hardware in first, get the whole part chromated, which makes that whole seal coat better, and there's no post-handling after your part's plated, so you have minimal scratching and minimal handling. This is all on our website, live. The dash number is actually step in 15 thousandths, so you can see the length code. It is very easy to find out, but again, as a quick reference, pop this up, and you know, if you need a half-inch standoff, it's a dash 16, and it's really quick reference. I actually still use it. So, as I was talking about, unless you really have FeatureWorks, when we do a countersink or a rivet with a countersink head, it's actually fairly difficult to get that snap to work all the time. So there is some workarounds, but I'm going to show you something that always works. And once you do this once to your rivet and save it in your library, you really only have to do it one time. And that way, every time you drag in a rivet, it's going to help out. We're also, and I'll show you the end result, and then we'll go back through and step through it. Files here. One is the standard hardware. You go to McMaster-Carr, you can download this off. And usually, who has done mate references before in the room? Great, this will be cool. When you download this from McMaster or the Penn Library, you don't get that mate reference all the time, right? So we're going to put a snap feature on, so when we drag the part in, it will auto-locate. On this, a common place that we've noticed people use it is you go to Insert, Reference Geometry, Mate References, and they'll pick the top point of this countersink, and they'll say OK for default. What this does is it does give you a self-guiding reference, but as I drag this over, it usually will tend to snap in like that. Has anyone run into this problem before? There is a keyboard shortcut, it's called Tab. You hit Tab and it should flip through, but every single time you drag this piece of hardware over, it's a two-step process to a tab. If we want to modify it, we can open the same part up again. So this is that same geometry. You can come up on the end, convert that outside as a sketch, extrude it down. We want to reverse the direction and go 0.5 thousandths, very small. We're going to do 1 thousandth. this edge, we're going to convert it, we're going to convert this line, and then we're going to cut this back 0.5 thousandths. It's very small cuts, but what we're achieving is we're achieving a line in between two 90-degree faces. This internally will tell SolidWorks what direction we want that to auto snap to. Insert, reference geometry, mate reference, and again, less is more here. We tend to see this mate reference really filled up. If you can get away with this one line and the two intersecting planes, it'll always work and your file sizes will be reduced, especially with rivets because you have so many rivets usually inside a large assembly. So now when I have that part modified and I drag it over, it'll always snap right to where it was. Very quick. With rivets, you have about 20 or 30 rivets in a part. So I mean, you want that process to be fast. The overall point is one line in between two 90-degree faces. You can do that for panel fasteners. You can do that for a lot of other hardware or anything that does not have a perpendicular slope. But again, you can see the end result is very fast and it works out pretty good. The next thing we would go over is flush hardware. Flush hardware is difficult because, as you can see, there's really only place to get that 90-degree line, and that two planes will be under the flush part. So when you snap this on, it's not going to sit flush. And in the PowerPoint that will be available online, this is very specific and laid out, so you should be able to follow the 3 steps. This is where we're at now. This is the usual point that we have noticed people choose, and this is the end result of that flush hardware, which really is fine. When you get your actual part, it will not look like that. It will be flush. And again, very detailed 3 steps on how to get that to sit flush and automate. We're going to take advantage of this top point. We're going to make a cut sketch, and then we're actually just going to take a sketch from this plane, extend it down, and use the same line in between two 90-degree planes. So as you can see, all we need to do is now put our snap point to this location. Pretty simple, but just a little different approach to how you're looking at it. But again, there's tons of different hardware out there, and you can use this approach to almost any of them. The other common problem we open apart we'll look at for countersink through hole sizes. And then another major thing is we have to ensure that the hardware hole size is a proper fit for the hardware inside the assembly. SolidWorks, I really believe this will be fixed soon, but today, if you want to walk out of here with a better solution to finding your hardware hole sizes versus looking at a chart, this is an option that you can do. Again, hardware, PEM hardware, is that really used by, commonly used? Good. And
I got a question.
Yeah.
Toolbox parts, usually they're read-only, they don't modify. You're modifying, right?
This is for people without the toolbox.
Oh, without the toolbox.
And you must have FeatureWorks, and that was my first question. With FeatureWorks, it comes with a toolbox, and a toolbox then, it's pretty interesting. It has one rivet, but it will auto-size to whatever through hole is in your part. So then you have a smaller library, more advanced. A lot of things that are common, not known, is someone that without that toolbox opens that part up, that rivet actually expands out and does not rebuild correctly. And that's something I'm sure SolidWorks will fix down the road. Anyone from SolidWorks here? we will get them. I'm gonna skip over this step and kind of show you the end result. But again, it's all in the PowerPoint, very step by step on how to get the end result. Actually, does everyone know how hardware is installed? This is just a cool little thing that someone did for us. The hardware thing, actually. Let's do all right, so I have a couple different pieces of hardware. The end result of my tree is nice and organized. You can see that this is for a 256 with a 167 diameter. This is for a 440 with a 167 diameter. So it's nice and clean, and it creates a very organized tree. If I was a manufacturer, I would not have to double check this. I would just say, hey, this is spot on, this must be correct. After you step through the whole wizard modification, you can actually get all that data inside your whole wizard. So when we make holes at Rapid Sheet Metal, we can simply pick which hardware we're making the hole for, hit position, create a 3D sketch, and we know we're going to be right every single time. What we also have done is the pen specs out a 344 plus 3,000ths minus nothing. Whenever you can, you should always split those tolerances, so we should use a 1,000ths larger, which is a 345. Any questions on that, or would you like to see that in more detail? It's definitely more advanced. I think when we get through that, we can do some more things. But again, everything's stepped through, and this will be available afterwards. This is going to be great. This will get you to be able to use form tools very fast. And we actually did all the hard work, which is coming up with the different shapes for louvers or embossments or half shears or bridge lances. It's always nice to have those features in your design. It's actually very difficult to design something that can be properly manufactured and that's available, that you can go to your vendor and not have tooling cost and add a lead time. We don't add any lead time to anything that you would choose off our website. This is our website again. Matt Sordillo over here did a great job in designing it. He has this nice interface here. If we come over to tooling, online tooling library, we have this in SolidWorks and Pro E. There is a video that we can go over and I can show you. But again, this will quick bridge lands. If you want any of these embossments, you can just simply download these on, and I'm going to show you how to quickly drag and drop these onto your SolidWorks files. Anything with a sheet metal feature will work.
Are these commonly available to all sheet metal
Yes.
shops? Okay.
So the things that we put on there are louvers, are embossments. They have the correct angle. It's manufacturer appropriate. With an embossment, there is a certain angle that you can get away with versus material thickness. So all that is accounted for. We can make these very easy. Other shops can make this very easy, and you're not designing yourself into a corner. So even though you use it from our website, other shops should easily have these sizes available. But we would like you to use it from our shop. So, any part with sheet metal on it, as you can see we have sheet metal on this part. I can do it right from an assembly. I can click edit. I can grab the bridge lance tool, drag it right onto my part. You can orient, put it wherever you want, flip the direction, and hit OK. And you have very nice simple wire ties. This is great for production, for wire ties and prototype. It's really good to use TD hardware.
Can you do that again?
Yeah, no, this is really powerful. And we can use different tools.
It's in your toolbox.
It is not. These are all on our website wherever you decide to save them.
No. Feature. Form tool.
You don't have to have them in your toolbox. You can actually drag them right off your desktop, which I always thought was interesting. Say you downloaded this to your desktop and you're not using it. You can do the loader. The loader is pretty cool. And again, we have a step-through video on how to do this right on the website. But you can see that's pretty cool. And if you come to us, we don't add any tooling charge, we don't add any extra lead time. You can still have this in 7 days. And I think if you're doing quantity one, it only adds about like $30 to your part cost, which is relatively cheap to getting a prototype of a nice vented out luber. So design your prototype as you want, and we will try and make our service cater to that. That's really why we've been very successful. Especially with feet too. You never want your boxes or your cabinets to sit flat on any surface. Anytime you can do 4 embossments, it just comes with a better design and more things that you rest down. You know, the bottom you get the nice air gap and everything else on there. All right. This was a video that, nice cut up short video. This is from the online video, but it's just cut down to be very fast. Does this seem pretty much right on target for you guys, or? And there probably could be a whole session just on this, the way you can, position it, flip it, rotate it. There's a lot of different things you can do. One of the common things is that, as someone posed before, how come the manufacturers don't just use my flat? Why can't, they just unfold? I've designed this stuff in sheet metal. How come you're not using, my features? A lot of times, it comes up with these settings right here. When you take SolidWorks out of the box, it's defaulted to pulling your flange lengths right off your radius. So now we have SolidWorks that's very advanced, and you can modify your radius and change your internal radii from like 030 to 060 to 090. But unfortunately, if any of these settings are on, you've actually changed the whole outside dimensions of your part. I'm going to show you an example of that. So what we do is we will do an overlay. So as you can see, this part compared to this part is spot on. So if I move one, the other one will not move. I can open this part up. This part has been designed in sheet metal, which is great. As a manufacturer, I would like to use an 030 instead of an 072. Doesn't look like anything alarmed out. You know, as far as I can see, it looks like it's the same design. When I'll come back to the overlay, you'll see that we just changed all his outside dimensions because it's linked to start and stop from that radius. So in a presentation, it would be nice if we can not use these three settings, because all these three settings actually link to your inside radii. There are some standard inside radii that every manufacturer uses. Wilson Tool is the tooling manufacturer house. That's where all sheet metal shops get their tools from. There are standard sizes that we have in the printout: 030, 060, 090, 120. And if we can tend to use those standard top sizes, then we wouldn't have to change. But to utilize SolidWorks, which is how it's meant to be, is where you can always change your values. Should we try and, if you can, stay away from using these settings. This goes into the material. SolidWorks has this awesome ability. You can just change and associate what material type is inside your part. It seems like a lot of people don't use this step. Does anyone in the room actually assign the material type to their parts? Great. So this is pretty familiar. You guys make your custom libraries, and this is what I think is very helpful. What we do, if you can make a sheet metal folder with these selected materials, it will be a great help. The part will come in, we'll be able to tell what material type it is, and that reframes. Everything is now in your 3D model, which I think the industry is going towards. The one thing they don't do is they don't ever add the finish. If it's chromate, if it's black anodized, or a spot for that, which is really a source on why you need a print and to pass this information along per part. Has anyone found another solution to that?
Custom properties.
Custom properties. And that's what I'm going to show you now, because as of today, walking out, the solution today would be to use this feature. And it's actually pretty cool once you have it set up. Custom properties, this is going to be a very overview, very fast shot at how to do it. And everything is stepped through on the PowerPoint, so you can come back and review it. And I'm going to do that now. But basically, the end result is when you open a part up, you'll be able to have a drop-down box to then input in your finish. And this will be then linked right to your print, which you can see down here. And if you call it finish, the standard out-of-the-box template, which is automatically link up for you, and there's no crazy, print template modification that you're going to have to do. A lot of people use the custom properties already. It is really helpful, and it's actually very simple to do now where it wasn't before. It's something that's been in SolidWorks for a while. Basically, I'm doing it from scratch. I have nothing set up. You can double click what different columns you want, or drag and drop. Call this finish. What types of finish, chromate. Chromate anodized. If you check this box, you can then go ahead and type things afterwards. If you choose this custom layout, this is the important part. Where do you want to save it to? I want to save it to someplace I'm going to remember. New slug. Call it template. Close this out. come to your properties. File location, and you'll come down to change your custom properties. To that same folder you just saved that up to. Hit OK. Now when you open the part up, you can click on this box at any time, select your chromate, hit apply, and now this actually gets saved permanently to your part file, which is now right here. You can see we put in the custom description, chromate, hit cancel, want to make a print of this. We had default templates. So these are the default templates which have finish in it. Take a part over. And you can see that it's already linked automatically to set for chromate. Which is really helpful, especially when you're working on other parts, or if you pass this on to another person, that you can then quickly change everything from your part model. Go ahead and edit your materials. This thing should be 50-52 aluminum. 50-52 aluminum should be used for sheet metal. SolidWorks really only has 60-61. Might have changed that. Yes, they did. Hit apply. And now you have your material type and your finish on your model forever. Whether that print gets deleted, you want to make a quick new print. It's just a very quick way of adding information to your print by your part model. You can add a ton of things to this list on this side. A lot of yes, no's. And the other big advantage, again, is if you come to our website, you can actually use the resource links, come down to plating, and we give you all the actual codes with a description. Basically, the difference between type 2 and type 3 is hard coat versus regular coat. And we kind of try to make that very transparent and spell it out. And then these are the different colors you can get in type 1 and type 2. This is also a very helpful resource. This is how sheet metal is formed. These are goosenecks. A lot of time you'll look at this and go, yeah, great, but I don't know what tool you guys have or what standard or how big my return flanges can be. Again, we put that information online. We have standard goosenecks from Wilson Tool that you can download, throw into your part, test your return flanges around and see if it's going to be a clearance issue or not. I think this is really helpful, getting the information that we have available to the guy designing the part. So here we have a basic part. It definitely looks pretty straightforward, a couple U-bends, but you can see that this gooseneck just is not going to cut it. And all you would have to do is, download and install are 3 goosenecks, and then you can go ahead and do this same test that the manufacturer is going to have to do to figure out if you can form it or not. Basically, if you had some of these, you would see that if we didn't have this back flange on, we could achieve that first bend with the, you know, these are Wilson tool numbers as well, with the 40503. I'm almost sure every manufacturer will be able to reference those numbers. If not, they're cataloged and they can, you know, get that tool within a day. So this isn't custom tooling. And standard goosenecks, whether it's this exact tool or not, it's going to be this size. They come in 3 sizes, and that hasn't changed in a long time. But I think this will be helpful, right? I mean, just bring the awareness up, and that way, especially if I'm a designer and I want to know how deep I can get, you really realize why we can't answer that question, because there's so many different variables to that. It depends on your open height versus your return height versus how much room we have in the back.
What if that's the actual design, you can't change it, and then is there, you have to make a custom tool and
It's a great point. Manufacturers have all these down and dirty secrets that once we let one out, the designer just loves it, right? So I can arm you guys with the absolute old school trick, but it would really only be beneficial for a prototype world or the quantity between 1, 5, and 10. What we can do is actually put a bend right here with a large radii, which moves the backside out of the leg. How many times does that happen in a room? Yeah, here we are. So it's a pretty cool trick. No manufacturer wants to know that you know that, but it is possible. Would it be possible in production run? When you're making a larger run, all these issues really do go away because a custom tool versus your runtime is not as painful. When you're making 4 or 5, you would not want to see a try of a custom tool. When you're making 100 or 200, it would actually save time versus doing this technique. Any other questions?
On your website, do you also have any standards as to, you know, whenever you're doing like forming tools, how close you can put them to a bend or anything like that?
Yep, it's pretty much on our website. There's a video that actually shows. I wanted to make it very visible on what happens when you do a bio like that, rather than just giving the rules. And it's called Rapid Techniques. And here you see some of these forming basics. What happens when a hole is too close to an edge? And it's actually a really cool video. We'll skip through it all, but it will show you what happens. Because how many times have you heard that hole is too close to an edge? But have you really seen it pull? And this is what we show. So in the printout, it has, well, just a reminder to go to our website. Square cutouts are hard when they're too close to a bend because you can't really machine out a square inside cut. It's very difficult. Again, there's workarounds. There's always a workaround. In the short run, we can do a laser kerf cut down the bend line and then weld it afterwards. In production run, it really should not be a problem because they're going to buy, again, the cost of tool pain versus the run is a washout. This is an example of the hole pulling or a laser curve cut. We can come back and weld that afterwards, and you probably wouldn't even really see that we did that. So this is what a hole looks like when it's too close to an edge. And it really has to do with the 3 pinch points. We always use a bottom die and a top die. And basically how sheet metal is formed in a press brake is just by pressure in between 2 points. Before the technology was good, everything used to be coined. And the other question that's very difficult to answer is why the inside bend radii and what should it be. And even though we use an 030 tool, it does not mean you get an 030 inside bend radius unless you coin it, which is by force. The newer press brakes are more sophisticated, so you can use dies that do not come all the way down. It's called air bending. Forming basics while we're on here. Actually, we'll give you a great picture of what I was talking about. Has everyone seen sheet metal being formed? Yeah. So pretty much that back gauge is really the intelligence behind the whole process. Rapid sheet metal, we're kind of leading the industry because we're using your 3D models to form your parts. By doing that, we ensure that we're within 3,000ths on our first bend, and then it's just small adjustments that our operators have to do. We can actually simulate all the bends before they're bent, and because you're using a 3D model, there is no human error involved, and that's why our quality is so repeatable and that we can deliver so many parts in a short amount of time. The open die width, does anyone want to take a stab on how wide that should be?
Say that again.
The distance between the 2 points on the bottom, or that open die width, we have multiple different widths for dies, and that should be about 8 times your material thickness. So if we take 8 times and divide it by 2, you come up with that 4 times material thickness away from the bend. And it just has to do with anything outside of that point. If it's not touching this point, it does not get formed. So then as the pressure comes down, that material will just dive right into the part. We have a really cool example of that. This is an animation, it crashing out. And this is also why all your sheet metal flanges should be at least 4 times the material thickness. So as you can see, that we're trying to bend something that's not going to hit that bottom, all those 3 contact points. And what happens is this. So again, the workaround is you have to add more material, machine it off, or go back to the design and try and get your flanges to be at least 4 times the material thickness. But it's really cool to see, the why. And this is what the guy's up against. And when it's borderline, there are some workarounds. But again, all of those things come into how tight of a tolerance we can hold. 60-61 versus 50-52. Have you guys heard why that's bad or good or indifferent? Who has actually seen it break? It's pretty cool. It's kind of deceiving. So it looks normal. It looks like it's formed correctly, but it has glass in it and it's very hard. So with minimal pressure, it's going to break after the fact. So when your manufacturer tells you, yeah, they can form it, but it's going to break, this is really what they're trying to explain to you guys. Can you form 60-61? Yes. You just need a very large radii, and it is a lot stronger than 50-52, but 50-52 is just industry standard. That's what sheet metal houses use. The other thing is if there's an ounce of welding on any aluminum part, it should be 50-52, because when you heat up the 60-61 material, it turns into 50-52. And that's also another thing that's not commonly known.
Is there an appreciable difference between H32 and H34?
It is a difference, but it's not that. It's not a major. It's in the tensile strength. MasterCard is a great resource for actually finding all those specs, and they actually detail that pretty good. Offsets. An offset is actually what happens when you have two bends very close together. As we showed, if I can go ahead and form this one in that manner, how am I ever going to get this other offset in there? And there's a whole other tool for that called an offset, which then coins the material, actually forms both at once. And this is that process being done. It's pretty cool. And there's all sorts of different offset sizes. A lot of the times when you use an offset or a jog in SolidWorks, you just kind of set it to the material thickness because you want your box to cover, to be offset by a material thickness. If you're going to go that route, if you use this is a 90-degree offset, if you set that distance in SolidWorks to 45, SolidWorks will not crash out, and it'll be easier for a manufacturer to use a larger offset but still obtain that distance that you're asking for. Who has used the offset command in SolidWorks?
I've actually had problems getting material thickness, single material thickness offset.
Good set. That's kind of what I was just talking about. Let me give you a little demonstration of that. So this is the cases where you want an offset, and it has to do with, again, as you mentioned, you want the outside dimension to sit flush, but you want an overlapping interface. What we have noticed is that this type of enclosure is becoming more popular versus a big base and a lid. With this enclosure, I mean, the design's been around for a while, but you can see how much more room you have to get in there, work with. Your board's on the bottom. You can do your fan in your work, and when you put the cover on, it is no different. When I open this up, you can see that we have an offset. As he was talking about, if I go to change this around, and I try and make this a 90-degree offset, which comes off as standard, you do get an error. This error is just saying that the minimum thickness can be 0.79. Where is that number coming from? That number is coming from a combination of your radii, which when you use offsets, you kind of saw how that gets crushed. The inside radius of an offset really has to be 8 thousandths. There is no 1/8 inch radii for offsets. No one makes those. If you're designing for something like that, that is custom tooling. Anything can be made, But whenever you use this offset command, the great default would be 8 thousandths. Change this around to 45, and you can then go and always have your material thickness.
It just creates a bigger gap between the main part and the bend of this part.
There are steps of offsets that you can get in 90 degree, and if you use a 0 radius, you can achieve that. And the way that you would do that is if you had 060 material, you would just make your offset 061 with 0 radius, and then you should be able to do that.
That's what I usually do.
Yeah, I mean, standard offset is 060, 090, 120, and then up to 213, which is a weird one. I don't know why they chose 213. I was going to demonstrate equations and how you can really just design one box one time. This is a very standard configuration. If I go to edit this part, you can see that we have the X, Y, and Z as equations. We spit out 3 numbers. Anyone call what a number? 7. And basically, it really doesn't matter. And I can show you that at first, looks like there's rebuild errors, but when you rebuild both parts, they're linked to each other. And this would really be beneficial if you're making this design with a bunch of configurations. You wouldn't really have to ever redesign it. Has anyone ever used equations? It's actually not hard. Basically, when you're starting your part off, you kind of have to do the same stuff anyway. You come to an edit sketch, hit Q. This is what an equation all linked up is. You can simply delete them. We're going to make new equations. That's what this global sign is. If you hit equals, it'll start the equation. So all you pretty much have to do is equals and like K. You get this dialog. You hit enter. Do you want to create a new variable? Sure. K is my new variable. Now, obviously, I have the other one unlinked. But you can go ahead and dimension K. So that's very straightforward with sketches, and it's nice and easy with sketches, but how do you link it to extrudes? Or even edge flanges? So now, you can see that I do have it linked to the edge flange. Go ahead and start from scratch. Because this, what I'm going to give you is if you ever start doing equations, which inevitably I think it's going to be there in a couple of years. Basically, you're going to start out the sketch, snap on your points, dimension equals, call this X, enter, enter. Now you can change your variable to 3. Dimension. Another not common thing that I thought was tricky, if I just click on this when I have this dimension open, it'll change that dimension. I thought that was interesting. You can square it up. Equals Y, enter, enter. Hit OK, hit OK. Now I'm going to extrude this off. I'm going to hit enter. Here is my equations that I just made. If I put height in here, do a height of 6, hit OK. Instant 3D has to be on. If you click on a part without Instant 3D on, you're not going to get the blue dimension. And you can see,
With instant 3D off, all you do is double click.
what do you do?
With instant 3D on, you just double click.
Thank you.
SolidWorks manufacturer.
So how do you get this dimension linked in? Oh, look at that. All right, well that's interesting. So if you're double click, that is the easiest way. If you're like me and didn't know that, you can right click and link your values. So there are a couple different ways to still link to the same, and when you hit rebuild, it'll then enforce that dimension change. But so far, this is not very difficult. So now, when we make an assembly out of this, save the part off. Make assembly, begin assembly. When I bring in a part from an assembly, you can instantly create reference points to it. You can start your sketch or convert your sketch. Extrude, 1 inch, hit OK. Now that is dynamically linked to the base of my part. I can click on Edit Equations after you edit your part. We want to change this maybe to 9. Rebuild. And then that part is supposed to change.
It happened because you saved your part, you created the part before the assembly is saved, so when you saved it, then it comes up and it's stupid.
But this is great for you guys to kind of see. I mean, you're going to try this at least once, right? So I went a little too fast. I didn't save my assembly first. So it didn't have any place to save that reference. So now if I just bring in that part again, insert component, click on the plane, convert it, extrude, hit rebuild, save. Edit the part.
You want to save that externally every time, then I'll.
Yes, this is, if you haven't known, this is not my computer. I just got this yesterday. So it's a little unfamiliar. All right. Change the base part. And rebuild, as you can see, it is now linked. The really amazing thing is you can have these equations a text file, so I mean anyone can go in there and say, hey, I want this electrical box, and 9 by 10 by 20, give me another one by 5 by 10 by 30, and all dependent about how you do your other equations, it should all change dynamically. And that's where this is. So here we have that same box. And again, this is a basic shell of a program. You save this, you draw this type of box once, save it off. You can come back and use it as a template, fill in your whole patterns. little things that I thought was interesting was the control copy that's been around for a while. The trim command, everyone knows the trim command. If you hold shift down and click on this and drag it, it turns into extend. Shift, click, drag, trim this up. Say that was very complex. I never knew this. If you hold the control button down, you can actually drag this feature. It's interesting. I don't know how much you would use it. I think it would be used instead of blocks or references, but if you had a very complex shape and you want it on another plane, it actually helps you get that to that different plane faster rather than doing blocks and templates and having to resave that geometry. So we have about a half hour left. Does it seem pretty much right on topic, or?
Question regarding SolidWorks here's its flat pattern for its press brakes, then lines are the center raise. Have you ever manipulated it so that you can generate a flat pattern where you use a box and hand brake so your end lines actually offset the side of the radius instead?
You can definitely do that. I mean, the way that you would do that is take your part to the brake, find out what the dimension was from where you started, and then take that same bend line SolidWorks gives you and offset that distance. So yeah, it's all very possible, and that is the difference between that as well. So yeah, 4 minutes left. And any other last questions?
Any issue about modeling a solid, shelling it, ripping the corners versus starting out as a base sheet metal, and then insert sheet metal feature versus starting at the base flange and then adding flanges?
I'll tell you what, I actually prefer that method. I can whip up some boxes really fast. If I was designing, I would probably do this. This is really the way that it started before. Can you offset this? Say we need a half-inch return flange, return, hit OK. We want to cut 0.062. Now I want to shell out this whole thing to 0.62. This is really how personally I would design a box, because the part we didn't get to is how your manufacturer is going to cut it up. And they will actually not start on this line. There is, when we need to weld that line, when you weld in a flat, there's an angle grinding tool. And when you make that weld right on that seam, you have to then hand file that seam out to a 90 degree. If you can make your cuts off to the side, then when we go ahead and weld that area, we can use very fast tools, especially in production. You just tap that off and you're not damaging that nice corner. So this is basically what we tend to get, and it's great. We can understand the concept of what the designer wants, but this is what I have to train my department to turn that into. And again, you can see that we want to tab everything off and keep that dimension off to the side. These tabs is actually a really cool trick for doing them. You can make a library feature that then you can go ahead and edit. So if I wanted 2 tabs instead of 3, They'll all be self-controlled.
Is that a shop preference or any standard user preference?
It has to, I think it would be a shop reference, but it really is the different type if you're doing steel, stainless, or aluminum. You can see it's, as manufacturers, it's just part of the process that we do have to always do to really seal that in. But there's very fast ways of doing that. And one thing I want to say about SolidWorks is if you find yourself doing the same task over and over, just try and block out some time or ask some questions on how to do that faster. You can learn SolidWorks in a month, but you never stop learning it, and there's so many tricks that you know, you just learn every day. I think that's... Let's go to 10:30, right?
Okay.
I'll show you one last trick. The convert sheet metal, it will usually always work on a part like this. Unfortunately, it won't. And we have to put in bend reliefs for it. Again, if you use a library feature, you can drag this over. You can drag this over. And you can unfold a part like this very fast.
Welder's not gonna like it.
This really wouldn't be how we would do it either. If we were quoting this part, this is what we use this technique for. Even as a manufacturer, there's two different ways that we unfold part. One for quoting, which all we really want to do is get a nice flat and a perimeter. The thing that we can't get when you provide us just a print is we can't get the perimeter, which is what we really do need for our laser times. But again, on daily practice, I told you guys how many parts we do. This is kind of how we use SolidWorks, is we use this for getting parts flat. We do save most of our things as an assembly. To sheet metal lower. But the one thing I did not do, the delete face command. Has everyone used that? That is probably one of our workhorses. But we use that to get everything back to clear corners, and then when you can apply sheet metal to a clear corner or a straight 90, you can then change the radius. And it also helps convert sheet metal